There will be a lot of places in our applications of integrals where we will need to evaluate a definite integral. Now, evaluating definite integrals, we've seen in the past that we could do either by the limiting definition of the definite integral or by the fundamental theorem of calculus. In this video, we are going to find the values of our definite integral using the fundamental theorem of calculus. And remember, the fundamental theorem of calculus says, if you have a definite integral where the integrand, that expression, that function that you're integrating, is a continuous function on a closed interval, and capital F is an antiderivative of that function over the closed interval, then your definite integral can be found by evaluating the antiderivative at the top limit of integration minus evaluating an antiderivative at the lower limit of integration. So I can actually find my numerical value for my definite integral through that integration process. Let's see that in these examples. So first of all, we have our definite integral from negative pi over 4 to 0 of secant squared dx. So remember that when we don't have the numbers on the endpoints of the integral symbol, that's our indefinite integral. And that's when we needed to find an antiderivative of the integrand and add the plus c. I got a family of functions out as an answer for those. When I have my numbers as on the integral sign, my lower limit of integration at the bottom and the upper limit of integration on the top, that's a definite integral, and my answer is going to be a number. So you want to remember, indefinite integrals answer is a family of functions, definite integrals answer is a number. Now, to use the fundamental theorem of calculus, I want to think about this first as an indefinite integral. So what function is an antiderivative of secant squared x? In other words, what function had secant squared x as its derivative? Well, that was tangent x. So an antiderivative of secant squared x is tangent x. But because I'm asked to do the definite integral, not the indefinite integral, I'm not going to put a plus c in end. What I'm going to do is, after I find an antiderivative of my integrand, put a vertical line after it and remind myself of what the lower limit of integration is and what the upper limit of integration is. So notation-wise, this is saying I have found an antiderivative, but I still need to plug points of integration. Now it's really important to remember that you're going to plug the upper limit of integration in for your variable minus plug the lower limit in for your variable. So I have the tangent of 0 minus the tangent of negative pi over 4. So then the tangent of 0 is 0 minus the tangent of negative pi over 4 is negative 1. And then 0 minus the negative 1 is 0 plus 1 or 1. So this definite integral value is 1. Next up, what's the definite integral from 0 to the natural log of 7 of e to the x dx? Find an antiderivative. So what function has e to the x as its derivative? Well, e to the x. So I did find an antiderivative. It's just for e to the x. It is its own derivative. It is its own antiderivative. I'm going to evaluate that from 0 to the natural log of 7. Plug your upper limit of integration in minus plug your lower limit of integration in. So that's e to the natural log of 7 minus e to the 0. And then remember, e to the natural log of 7, well, the exponential function base e and the natural log base e are inverse functions of each other. So e to the natural log of 7 is just 7 minus, and e to the 0 is 1. Any non-zero number to the 0 power is 1. So then 7 subtract 1, I get a definite integral value of 6. Next up, my definite integral from 0 to pi over 4 of sine 2x. Now, this is going to require me to do a little bit of work with a u-substitution on it. So remember, when I'm looking at an antiderivative for my first stage and then plugging in the numbers, I need to think back to how I would have integrated that with my indefinite integrals. And the sign acting on 2x is an expression whose derivative is other than 1. And when you have an action on an expression whose derivative is other than 1, you want to make sure that you're getting correct antiderivative by using a u-substitution. So sine is acting on 2x. What's being acted on is your u. So if u is equal to 2x, then do your differential, du is equal to 2 dx, and sine will be u here. I have the dx, but I don't have the 2. So I'm going to divide that numerical factor of 2 to the other side. I'm going to need to put in a 1/2 du when I take out the dx. Now, this also affects what I have in my endpoints. And I can do this one of two ways. I can integrate it with u's, reminding myself that I need to go all the way back to x's before I plug in these numbers. Or I could transition my endpoints of integration also to what they would be in the u variable and plug it in there. I'm going to remind myself of what they were with the x variable and then come all the way back out and then plug them in, just so you can see it that way. In later examples, I will also describe how to do that with the u substitution and also switching those over so you see it either way and you can make your own decision what makes more sense to you. So when I do this then, I need to remind myself that these endpoints are in the variable x. So I'll do the integral from x equals 0 to x equal pi over 4. And then make your substitutions. Look over at the work you had written down on the side to remind yourself of what you've assigned in the substitutions. So 2x is going to go out and u is going to go in. So this will be the sine of u. And when dx comes out for its replacement is 1/2 du. So now when I look at this, the 1/2 factor can be brought in front of the integral. So I have 1/2 times the integral x equals 0 to x equal pi over 4 of sine u du. And I had to still bring the integral and the du down because I haven't integrated yet. That's what we're going to do now. So what function had sine as its derivative? Well, negative cosine. So this is 1/2 times negative cosine u. And normally we would do the plus c when it was an indefinite integral. This is a definite integral, so we're not going to put the plus c. Evaluated x equals 0 to x equal pi over 4, reminding me to go all the way back to x's before I plug in my values. Now that I've integrated, 1/2 times negative cosine u is negative 1/2 cosine u. Remember, that's multiplication. U is representing, standing in for 2x. So I'll go back to my x's that way. So I have negative 1/2 cosine of 2x evaluated from 0 to pi over 4. So now that I've gone back to the x's, I can just go from 0 to pi over 4. So plug in your pi over 4, so that's negative 1/2 cosine of 2 times pi over 4 minus negative 1/2 cosine of 2 times 0. Well, 2 times pi over 4 is pi over 2. the cosine of pi over 2 is 0. So I have negative 1/2 times 0, and this is minus a negative, so plus 1/2 times, well, 2 times 0 is 0, and the cosine of 0 is 1. So this gives me 0 plus 1/2, or 1/2. So my original definite integral is equal to 1/2. Let's look at some more examples. So for these next 3 examples, again, we are going to use the Fundamental Theorem of Calculus in order to find the definite integral values. And that, again, is you find an antiderivative for your integrand, and then plug in the upper limit of integration through your antiderivative minus the lower limit of integration through your antiderivative. Now, this first one has 2 different terms, but with definite integrals, we can do term by term integration, and that's also true for indefinite integrals. And then we will plug in our limits of integration. One of the first things we're going to do is rewrite this radical notation to its equivalent fractional exponent notation. So this is the definite integral from 0 to 8 of sine x plus x to the 1/3 power dx. Now, I see that they're separated by plus in between, so I can think of these as term by term. Each of these are acting on an expression whose derivative is just 1, so I don't have any u-substitutions for these. An antiderivative for sine x is negative cosine x. An antiderivative for x to the 1/3 power, well, that's letter-based to number exponent, where my number exponent isn't negative 1. So I just add 1 to that exponent. 1 plus 1/3 is 4/3. And then I divide by 4/3, which is the same as multiplying by 3/4. Now, because this is a definite integral, not an indefinite integral, I don't put the plus c, but since I've already integrated, I'm not going to write the integral symbol in the dx anymore because I've done that integration. But I haven't plugged in yet, so I'm going to put that vertical line, reminding myself it's integrated from 0 to 8. Now we're ready for plugging it in stage. So we're going to take out the variable and put in 8, and then minus, take out the variable and put in 0. So we have the opposite of cosine of 8 plus 3/4 times 8 to the 4/3 power, and then minus, and this is going to have more than one term. So when I do that second part, when I subtract off an antiderivative evaluated at the lower limit of integration and it's more than one term in your antiderivative, you need to put parentheses to make sure you're subtracting the entire thing. So put in the 0, that's negative cosine of 0 plus my 3/4 times 0 to the 4/3 power. Okay, now we'll evaluate this. Well, negative the cosine of 8 is just negative cosine of 8 radians. I don't have an exact value in a better form than this, so I'll leave it that way. If I were to approximate the overall definite integral at the end, I would want to make sure that my calculator is in radians to get that approximation. Now for the next term. Remember that 8 to the 4/3 power, well, the denominator of the fractional exponent is your root, and the numerator is the power you will take that root to. So the cubed root of 8 is 2. 2 to the 4th power is 16. So this is 3/4 times 16 there. We'll come back on another pass and simplify it a little bit more as we go. And this is then minus, and in parentheses, this is negative the cosine of 0. Well, the cosine of 0 is 1. So this is negative 1. And then my 0 to the 4/3 power is 0, 3/4 times that is 0. Okay, so now I have negative the cosine of 8. 3/4 times 16 is 12, so plus 12. And then minus a negative 1 is plus a 1. And so my final exact result, I'm going to have negative cosine 8 plus 13. I'm going to actually write the 13 term first. So 13 minus the cosine of 8. Just to make sure that it's just a little safer to write that way and nobody like extends the application of the action of cosine further than it's supposed to be. So that's my exact numerical value for this definite integral. So that definite integral's answer is a number. Okay, next one. This is the definite integral from 1 to 5 of x minus 2 dx. Well, remember we want to find an antiderivative of this x minus 2 and then evaluate it by plugging in the 5 minus plugging in the 1. So think indefinite integral first, just don't put the plus c. So two different terms. If there were a power here, I would need to multiply it out or use substitution or something like that. But here it's just to the first power, so I'm going to just do term by term integration. The integral of x dx, remember that's x to the 1, that's letter base to number power. Add 1 to the exponent and divide by that. So it's x to the 2, and then divide by 2 is multiplying by a half. And then minus the integral of 2 dx is 2x. And I'm going to evaluate that from 1 to 5. Plug in the 5. That's 1/2 times 5 squared minus 2 times 5 minus, plug in the 1. 1/2 times 1 squared minus 2 times 1. So then this gives me 5 squared is 25 times a half is 25 halves minus 10, and then minus, in my parentheses, 1 squared is 1 times a half is 1/2, and then minus 2. Distribute the negative sign. I have 25 halves minus 10 minus 1/2 and then plus 2. And I like to do this instead of getting common denominators and out of the whole thing and working it that way, because sometimes some of the fractions actually will combine and be where the simplification is an integer value, and it makes the calculation easier. So when I think about this case in point, 25 halves minus 1/2 is 24 halves. So that's going to be 12. So it just was better than getting everything to be in halves and then looking at it at the end. So I'll write it so that you see. So it's 25 halves minus 1/2 minus 10 plus 2. So that's 24 halves. This is 12 minus 10 and then plus 2. Well, 12 minus 10 is 2 plus 2 is 4. So this just gives me 4. Then the next one is the definite integral from 1 to e to the 5th of 1 over x dx. Well, if you remember, just rewriting it, the integral from 1 to e to the 5th, 1 over x is x to the negative 1 power. Remember, we cannot integrate with variables in the denominator of the fraction. We either have to rewrite it so they're in the numerator or have a u-substitution in some of our situations. But this is letter-based to number power where my number power is negative 1. If I try to add 1 to negative 1, I get 0. And I can't divide by 0. You add 1 to the exponent and divide by that. But if that process makes you divide by 0, that's like your aha, oh, that's right, that's the one that goes back to the natural log of the absolute value of your letter base. So the indefinite integral of my x to the negative 1 is the natural log of the absolute value of x, and if it were the indefinite integral, I'd add the plus c, but I'm working towards the definite integral. So I'm going to write that natural log of the absolute value of x, and not plus c, but evaluated from 1 to e to the 5th. And then just like the fundamental theorem of calculus has been applied to all of the other definite integrals that we've done as examples, you're going to evaluate it at the top limit of integration minus the bottom limit of integration. So this is the natural log of the absolute value of e to the 5th minus the natural log of the absolute value of 1. Well, e to the 5th is a positive number. So the absolute value of e to the 5th is e to the 5th. And the natural log of e to the 5th is 5 minus the absolute value of 1 is 1. The natural log of 1 is 0. So I have 5 minus 0, which is 5. Now let's look at how in certain situations we can actually find the area of a region between that function and the x-axis over an interval using our definite integral. Alright, so let's look at this and see if it's even a question where we can directly set up one definite integral to answer this. So it wants me to find the area of the region enclosed by the function f of x equals x squared minus 1. The x-axis, which also could be given to you in the equation y equals 0, on the interval, closed interval from 2 to 4, which also could be given to you as like the boundaries of x equal 2, x equal 4. Well, the first thing we want to do is to look at the graph of this and see where the function is lying over that interval. So f of x equals x squared minus 1 is a parabola pointing up with its vertex at 0, negative 1. And then it also has x-intercepts at plus 1 and minus 1. So I have my parabola that looks like this. And my intervals from x equal 2 to x equal 4. So over this interval from 2 to 4, this graph is above the x-axis. So the region that we're talking about is at x equal 2, so a vertical line at x equal 2, a vertical line at x equal 4, and then the function f of x equals x squared minus 1, and the x-axis, or y equals 0. So if I take all of those boundaries in account and look at what would be enclosed by all of that, we're talking about that region right there. Now, when the graph is on or above the x-axis over the interval, so when the function is non-negative over the interval, the definite integral number value you get out is going to be the same as the square units of area enclosed by this region. So instead of having to do that limiting process for area that we had to do in our previous work with the area of a region enclosed by a function over an interval, a non-negative function over an interval, I can just evaluate it using the definite integral. One of our first introductory applications of our integrals. So setting up the definite integral for this, my area is actually going to be equal to my definite integral from 2 to 4 of the function x squared minus 1 dx. And again, it's because my function is non-negative over this interval that the definite integral numerical value is going to coincide with that area. So now we're just going to do the same thing we've been doing on our earlier examples. We're going to first find an antiderivative for the integrand. And so that's going to be 1/3 x cubed minus x. And remember, we're not going to put the plus c because it's a definite integral instead of an indefinite integral. Instead, we're going to evaluate this from 2 to 4 and then put in the upper limit of integration minus put in the lower limit of integration from what the Fundamental Theorem of Calculus tells us that we get our numerical value from. So this is 1/3 4 cubed minus 4 minus the 1/3 times 2 cubed minus 2. And then my 4 cubed is 64. So I have 64/3 minus 4. And that's minus, and 2 cubed is 8. So that's 8/3 minus 2, still in the parentheses. Now I'm going to distribute, remove my parentheses. I have 64/3 minus 4 minus 8/3 plus 2. And then 64/3 minus 8/3 is 56/3. And then my minus 4 plus 2 is a minus 2, but I can write that as negative 6/3 for my minus 2. And then 56/3 minus 6/3 is 50/3. And so that area is 50/3 square units of area. So if you were to take graph paper and very carefully graph out this region and count your square units of area through that, your counting of your square units of area there would be an approximation of the area, and that would be right in the ballpark of what your exact value of your 50/3 square units value gives you.